This video is about the Doppler effect. If you have been waiting for a train, you know that when it's coming toward you, it makes one sound, and then it passes you, and suddenly the pitch drops a lot. That's because of the Doppler effect. The Doppler effect is the change in the apparent pitch, or the perceived pitch, as a result of the relative motion of the source and the observer. That's a lot. We're going to get a simple equation first. Not so simple equation, but we'll make it simple. The observed frequency is equal to the frequency of the source times the speed of the wave plus or minus the speed of the observer over the speed of the wave plus or minus the speed of the source. That is not a simple equation. It's got a fraction in there and two plus minuses. Regular v without a subscript is the speed of the wave. And then anything with an O is observer. Anything with an S is source, and the one saving feature of this equation is that at least it's alphabetical. The O goes on top, the S goes on the bottom. So here we go. What do we do with this? If I am standing here throwing water balloons, and I can throw one balloon per second, and then someone's over here just standing still, they are getting hit once per second. In this case, this is the frequency of my source, and this is the frequency of my observer, and both are standing still. V source equals 0, V observer equals 0. That's an easy one. If my source is running toward my observer and throwing one per second, and my observer is standing still, I am now getting hit more than one per second. Because I throw the first one, and then it's in the air, and once I've thrown my first one, by the time I throw my second one, I'm now over here. So now these are getting closer together. I'm getting hit more often than I was, which means for this one, I am increasing my frequency observed. If I do the opposite, if I am backpedaling and still trying to throw, so in this case I was running forward. If I am backpedaling and still trying to throw, now my observer, who is still standing still for the moment, is getting hit less than one per second, because I throw the first one, and once I've thrown the first one, now I move back, so that second one has a farther distance to go, and it takes longer. I'm not changing my throwing speed, I'm just one per second. So now I am decreasing my observed frequency. I want to relate this to my equation. So in both these cases, my observer speed is 0. Frequency observed equals frequency source. Observer speed is 0, so the top is just going to be V. The bottom is going to be V and V source. And I just need to decide, is this a plus or a minus? In the first one, I need and I got there intuitively. I need my observed frequency to be increasing. All I can do is mess with the bottom of my fraction. If the bottom of my fraction gets smaller, then the whole fraction gets bigger. Right? If I have 1 over 5 versus 1 over 4, 1 over 4 is the bigger one. So if at the bottom of my fraction gets smaller, then the whole value gets bigger. Which means I would like a minus there. Opposite here, if I want my observed frequency to be decreasing, which I can get to logically without doing any math at all, if I want my observed frequency to be decreasing, I need the bottom of my fraction to get bigger, so I'm going to throw a plus sign on there. That was with just the source moving and not the observer. Now I'll do the other part. What if my source is standing still? Still 1 per second. And my observer is running away. Now my source is stationary. I'm going to be hit less than 1 per second because, yes, I get hit with that first one, but by the time the second one comes, I'm farther away. It has to travel farther, so it's going to take more than 1 second for that second one to hit. Which means I expect here my frequency of the observer to decrease. Do the opposite one. If my frequency of source is staying at 1 per second and my source is stationary, and I go charging at my source, this is V observer, I'm now going to be hit more than 1 per second. So my frequency observed is increasing. And now I want to see what that looks like in equation form. FO is Fs. I'm now not messing around with the source at all. That speed is 0, so the bottom of my fraction is just going to be V. And the top I've got V, and I've got V observer. And I'm just going to copy paste this equation for now, because I'll need it twice anyway. All I have to do is decide whether I want a plus or a minus there. If the frequency observed is going to decrease and I'm messing with the top of my fraction, I can make the whole value smaller by subtracting in the top of my fraction. So I want a minus sign. If my observed frequency is going to increase, then I want a plus in the top. Those are really all the cases that I can possibly be working with. I'm going to do one where I've got the source and the observer both moving and see what that looks like. Let's say I have a source who's running like this. And I'm going to have an observer who is running away. Now, whether my frequency increases or decreases, whether my observed frequency is greater than or less than 1 per second, depends on these relative speeds. I'm going to start with my same equation, but now I get no zeros at all. V observer, V source. But this part isn't bad. I'm going to start with the observer, so I'm going to ignore the source. Let's say the source, let's pretend for a moment the source is standing still. If the observer is running away, then my frequency observed should be decreasing, which means I want a minus in the top of my fraction. Next, I'm going to hold the observer stationary. If the source is running at the observer, then my frequency will increase. To get the frequency to increase, I need the bottom of my fraction to be getting smaller, so I need a minus on the bottom of my fraction. So all I did was cover up the 1 and look at the other, then cover up the other and look at the 1, and I can put those pieces together. If the source is moving faster than the observer, then I'm going to get an overall increased frequency. If the source is moving slower, I'm going to get an overall decreased frequency, and if they're both moving the same speed, like my speed of sound is going to be 340 meters per second, if they're both moving 5 meters per second, I'm going to get 335 over 335. This whole fraction is going to equal 1, and my observed frequency is equal to my source frequency. That's the Doppler effect with water balloons, and that's also the Doppler effect with waves.